Today we're going to talk about composition of functions. Now, you've probably seen function composition at some point in your mathematical career. So what we're going to do is a little bit different because we'll be formally defining function composition with regards to sets in general. You've probably dealt with function composition on the real numbers. We're going to do it for any set, not just the real numbers. And we'll also prove some properties about function composition. So when we have non-empty sets A, B, and C, any non-empty sets A, B, and C, and we have functions f from A to B and g from B to C, it's possible to create a new function from f and g called their composition. So if we say we have the composition g of f and g, it's the function from A to C defined by g of f of A. Now, order of operations, we do what's in the parentheses first, so we first apply the function f, and then we apply the function g. So the domain of the composition will be the same as the domain of the function f, and the codomain of the composition will be the same as the codomain of the function g. So let's take a look at an example. So say I have a set A, the numbers 1, 2, 3, 4, a set B, the letters A, B, C, D, and a set C, the letters R, S, T, U, and V. And then we define functions f and g such that f is the set of ordered pairs 1b, 2d, 3a, and 4a, and g is the set of ordered pairs au, br, cr, and ds. Now, what we're going to do is first apply f and then apply g. Notice that the codomain of f is the domain of g. So this is set up that we're able to actually do the composition of functions. So we're going to do g of f, and g of f is going to be a set of ordered pairs where the domain, the first element in the ordered pair, is going to come from f. So f has 1, 2, 3, and 4. So g of f will have 1, 2, 3, and 4. And then the second element will be some element in C. So it's left to us to figure out what element in C that will be. So say we first look at g of f of 1. Now what we're going to do is we're going to look at f of 1, and f of 1 is b by my function f. And then I'm going to take g of b, and if I look at my function g, then b maps to r. So that means in my function composition, g of f1 is going to map to r. So 1r, that ordered pair, is an element of my function g of f. Similarly, I can do this for g of f of 2, finding that 2s is a part of my function composition, and I can complete the map for everything directing through, and I can see that g of f is the set of ordered pairs 1r, 2s, 3u, and 4u. Now, this is probably the type of function composition you've seen before. This is a common thing in calculus, where we're looking at functions that are on the real numbers. So I might have f of x equals x squared, and g of x equals sine of x. So we can look at g of f and f of g. So g of f says we're going to do f of x first, and then we're going to do g of x. So we're really taking g of x squared, which is the sine of x squared. Now f of g of x says we're going to do g first. So we're really taking f of the sine of x. So we're squaring sine of x. So we have sine squared x. Now notice, in both of these cases, the codomain of F matches the domain of G, and the codomain of G matches the domain of F. So both G of F and F of G are defined, but they're not necessarily equal. So the order that we combine our functions, that we compose our functions in, matters. Now let's take a look at a property of composition of functions. So we have a theorem. We have a function f from a to b, and g is a function from b to c. Now, if f and g are both injective functions, then so is g of f. And if f and g are surjective, then so is g of f. So we're going to prove this. We're going to let f and g be both injective functions. Well, then what we're going to do is we're going to do the proof technique that we used for proving that a function is injective. And we're going to assume that for two different elements in A, g of f of that element is equal. So we're going to have g of f of A1 equals g of f of A2 for A1 and A2 in A. Now, by definition, g of f of A1 is g of f of A1, and g of f of A2 is g of f of A2. Now, since g is injective, then we know that f of A1 equals f of A2, since g of f of A1 equals g of f of A2. But then since f is injective, we know that A1 equals A2. So that means that if we have g of f of A1 and g of f of A2 equal to each other, A1 and A2 are equal to each other, and g of f is injective. Now let's take a look at the surjective option. So we've got f and g are surjective functions. F is from a to b, g is from b to c. And we're going to take some element in c. Now, since g is surjective, then there exists a b in b, an element b in b, such that g of b equals c. Now, on the other hand, f is surjective. So if I have some element a in the set A, then there's an f of a that equals b for the element b in the set B. So g of f of the element a is going to equal g of b, which equals c. So g of f is also surjective. Now, a corollary of this, if f and g are bijective functions, so they're both injective and surjective, then g of f is bijective. It's a direct result of that theorem that we just proved. Now, here's another theorem that we're not going to go through the proof here, but the proof would look similar to the proof that we did with the previous theorem. So for non-empty sets A, B, C, and D, we're going to have a function f from A to B, a function g from B to C, and a function h from C to D. Then we can do h of g of f. We're going to group together h of g and then do of f, and it equals h of g of f grouped together. So we basically have this associative property of composition of functions playing out. Now, proofs with composition of functions look kind of similar, where we're going to use properties of f, g, and h, and we're going to do some element tracing back and forth across our functions. So think about how you might prove that theorem, and we'll talk about it later.